Okay, I think it said that we are live now. Welcome everybody. Welcome to the Bioconductor 2021, and this is the long workshop session. It's for dimension reduction for beginners. First, though, a few housekeeping items. There is, if you want questions for the speaker in the right tab, there are two different ways to do it. There's a general chat that goes out to everybody, and you can do that there. Though if you have a question that you want to be answered, you can put it in the Q&A. We can't answer them directly in the Q&A. We'll probably put them back in the chat, but then we can mark to see which ones we have actually answered or not. You can potentially raise your hand if you want to, and we can invite you on the stage if you want to ask a question live or interact that way. Okay, let's see. There's emoticons on the bottom. Some people have already seen that. If you want to give feedback, which is very nice, there we go. You found them. If you need to leave early, there will be a video of this session available within a few hours afterwards. So we haven't seen that, but I think if you go back to the session, there'll be a little button on the session. Okay, so let me introduce you to the speaker. This is Adine Culhane. And you are at the Dana-Farber Cancer Institute. Now I can see yours up at the bottom, which is really nice. And so she is going to give her long workshop. I will pin in a minute here, as soon as she starts talking, a link to her main slides, and then we will walk you through how to get up and interactive with the workshop. Okay, you can take it over, Adine.
Hello, good morning. Welcome to the start of the meeting and the start of the long workshops. I'm really excited to be kicking this off. And I will be doing a beginner's introduction to dimension reduction. So I'll just give you a quick how to find everything and how to start everything. So let me work out the share screen button again, okay. So if you go to Orchestra, we can start the session. If you can't see it, if you click on Created, you can select the more recent ones, or if you put in Dimension Reduction up here, then you basically should see it. So it's app.orchestra.cancerdatasci.org. Okay, and so it will take a while to launch if you have not launched a session already. So just click here on Launch, and in the meantime, I will go through that again. So this is a workshop on principal component analysis. And again, to run this workshop, we go to app.orchestra.cancerdatascience.org. You can also look at the markdown and the HTML packages from the GitHub link here.
We can one at a time.
So as I mentioned, go to app.orchestra.cancerdatascience.org, click on the dimension reduction and click on Launch here. When you go to Launch, it will come up with a username and password. The username is RStudio. The password is RStudio. This will provide you a link. The link is unique. Don't share it with anybody or they will kick you off of your session. So equally, I'm not going to share you my link because that will kick me off of my session. So please launch your own session to follow along. It will take a few minutes to launch. And so while that's happening, I will just give a little brief introduction. Again, don't share the link of the session. It's yours uniquely. You have it for, I think, 8 hours. Okay, so this workshop includes 4 different vignettes. Okay, and these are underneath the articles. If you're on the GitHub page, there's 4 different vignettes here. Equally, if the RStudio window has started, if you go into your packages part of RStudio here, if you click in PCA, you'll see PCA workshop. If you click on that, you can see user guides, package vignettes, and other documentation, and this here will bring you to these vignettes. Okay. So The 4 components within this, and we'll do them all to greater or lesser extent. The first is just an introduction to principal component analysis. And I think within it, I tried to address one of the primary questions that a lot of people have, which is what's the difference between singular value decomposition and principal component analysis. The second vignette talks about different flavors of principal component analysis, and specifically principal component analysis of a covariance versus a correlation matrix. And it runs through many different functions in OR that can do principal component analysis, and I show how to actually compute the same thing from all of them, what's the association with them. Next, we talk about correspondence analysis, which is a decomposition method for count data. And finally, we look at applying these methods to single-cell RNA-seq data. Okay. So matrix factorization or dimension reduction, including principal components analysis, are commonly used, and they're well suited to finding known and unknown or hidden latent patterns in large data sets, particularly wide data sets. Most of these methods, and definitely most of the classical methods, achieve this by something called, by an eigenanalysis called singular value decomposition, where a matrix is composed into 3 matrices: the U, the V, which are the left and right singular values, and the diagonal matrix here, which is all zeros except for the diagonal, which are the weights of the eigenvalues of the singular values of the matrix. Okay, so I am hoping that that segue was sufficient for you to launch your orchestra session. And so let's look at the first vignette. So the first vignette that we'll look at examines a very small data set. And this is actually from the ADE4 package in R, and it's actually called Bordeaux. And what it does is there was 200 judges who tasted 5 different wines, and then they scored these wines as excellent, good, mediocre, or boring. Now, just a little bit of background into French wines. The table wine are the wines that have the least amount of regulations and tend to be the cheapest, and the Cru or the Grand Cru wines tend to have the most regulations and tend to be more expensive. And so we can kind of see this, that these are the more excellent wines, and then the mediocre wines are the brand wine, the Vin de Marque, or the Vin de Table. And apologies to everyone for my dreadful French accent. Okay. So I am going to go into Orchestra here, and I'm going to open the HTML for the intro. Okay, cool. So we can open the HTML. We can also open the OR document here. Sorry, that's the HTML. Sorry, the source code as well here, if you want. Okay, so you can see the source code. We can see the HTML document. And if we click on the files here, we can also open up the RMD file down here. So it's up to you which way you do the code. So I'm just going to copy. I just ran the first copy and paste here, which is to load in the different libraries. We have ggplot and Explorer, which are visualization packages. ADE4 provides the data set. I've got some Tibble and dplyr for manipulation of the data, as well as reshape. Okay, we could probably use tidyverse as well if we wanted, or as traditional. Okay. So principal component analysis provides methods for distinguishing the patterns or information in a data set, and this is just a short taster. And I mentioned it is on this wine data set. Let's have a look at this wine data set. So data Bordeaux, if I click on this little arrow here, or you can copy and paste, copy, Control-C, Control-V, copy and paste here, or I can click in the RMD. I can actually visualize what's in the data set. And this is exactly what I was describing, as well as the 5 different wines and the scores of the different judges. Okay. This just shows us how to just generate a little table to change the wide format to a long format. And this can be useful when we actually want to visualize something on ggplot. This little bit of code here you don't need to run, but what it does is it generates this figure here. And this was simply me doing a bar plot of the data, but I can just do this, the simple version of it here for you, just so you can see. And if I draw a P, okay, and I can see my plot. This is the standard bar plot, but because I had a little bit too much time the day that I was looking at the data, I decided to use a fancy GG theme on it, and I used this homological theme, which generates this really, really pretty little figure with italic text, and it doesn't look like it's been generated in R. But we can clearly see here that the Cru and the Grand Cru wines have more excellent scores compared to the table. Okay, so we're going to run PCA on this. Now, as I haven't quite mentioned, I said that this can be computed via singular value decomposition, but the thing about principal component analysis is we first of all scalar center the data. So let's actually scale the data. Okay, so this function here, scale, where centering equals true and scale equals true. Okay. And now we actually have centered and scaled data. And then we can run SVD to generate those 3 matrices, the diagonal matrix D and the singular vectors V and U. Okay, we notice that the V singular vector here has got 5 rows, and sorry, the U, and the V has got 4. And that's because these are the 5 singular vectors corresponding to the 5 wines, and the V here is the columns, the singular vectors corresponding to excellent, good, mediocre, and boring. Okay, to prove that if I multiply out these 3 vectors, I regenerate X. I can look here, and this should be the same as my scaled data. I'm looking here at my values. So multiplying U, the singular vectors in U, the diagonal matrix D, and the singular vectors in V, we regenerate this. So these 3 matrices multiplied together give us our scaled matrix. Okay. So what's the diagonal matrix? The first one, D. This is actually, if I just do $D, it's a vector, or I can just diagonalize it here where everything is 0 except for this diagonal. Okay, these are my singular values.
Eileen, I decided to throw a poll up real quick to see where everybody is, if they're keeping up or how many people are still behind.
Thank you.
That's not too bad.
I don't see the results. Where are they?
Okay, we are running about 40% are keeping up with you directly. 30% are running codes, but they're a little bit behind you, and then 25%-ish haven't still gotten it going or found the VIN yet.
Okay, well, let's actually make sure that everybody finds it first. So that's actually.
So I'll close the poll so we can see you.
Thank you. That's a really good idea. Thank you for doing that. Whoa, that's interesting.
Yeah, that's the mirror effect. Let's see. I will hide myself again real quick.
Okay. So for anybody that hasn't found the workshop, okay, it's, let me just, if I open up IOC 2021, I can click on schedule and I can go to workshops here. Does it link to the, oh, it doesn't link to the orchestra there. Okay.
There is a link in the chat. to go
I was
to
trying
the,
to see where is the actual link to the orchestra platform from the website. It actually isn't, is it?
it's somewhere, but I'm not sure where. But at the
Okay,
very beginning
so
of our chat,
let's
like
ignore
the
that. I thought
second,
it might be there, and that might be a helpful place for people. The actual, I just closed something there. The actual link is app.orchestra.cancerdatasci.org, and the link is actually here in the chat window. So if you actually are on the platform AirMeet, and I know this is kind of a funky mirror effect going on here, if you actually go into the chats, you will see that the app.orchestra link is actually linked here as well. Okay, so app.orchestra.cancerdatasci.org. And when you get there, click PCA, or sorry, Dimension Reduction, DIM, and you'll see Dimension Reduction for Beginners. If you click on the link, it will actually bring you to the GitHub page, and you can definitely follow along with the vignettes here and copy and paste the code in. But you may not have loaded all of the libraries into your own local R session. If you want, you can install this package. It's just DevTools install GitHub AD PCA workshop, and that should install the package and its dependencies. Or if you've got your orchestra session working, you can just click on the launch button here, and that will launch an RStudio. So click launch, put in the password RStudio, username RStudio, all lowercase, RSTUDO, username, same password, and then that will launch an instance on the cloud of RStudio in which all of the required libraries are available. Okay. Jenny, do you think we're doing better, that everybody has at least found it? Ooh, I like the emojis. They're looking better. If anybody's not found it, if you want to do a really sad emoji. Okay, we don't have many sad emojis. Okay, let's get going. Oh, that's kind of fun, isn't it? Oh, the crying, laughing one is really bad.
There's one question. I don't
Yes.
know if you want to see the Q&A, if you want to handle that real quick.
I can't see it. Where is it?
It says, how do you decide whether you scale row-wise or column-wise? It's in the Q&A section rather than the chat.
So with PCA, so we're calculating it. I'm just calculating it out scale manually, and then I'm actually running SVD. If you run any SVD function in any R package, it always scales column-wise because it assumes that you're dealing with a wide matrix. Okay, but I will talk a lot more about scaling in a few minutes, and I'll get into a lot more detail on that, and also ways where we can actually look at rows and columns together.
Okay, and there's one other Q&A. I don't know if you want to handle that. If you click on your Q&A tab to the right after, yeah.
How do you decide? Okay, from the linear algebra perspective, I understand what singular value decomposition is doing, but I'm not sure why we need to do it, because singular value decomposition gives us a different representation of the matrix, in which, and I apologize for background noise here, in which the first vectors represent most of the variance in the data. And it allows us then to generate a low rank. So the rank of the matrix is either the number of rows or the number of columns of the matrix, whichever is lower. So it's the lowest way you can, or it's the representation, the dimension of, the lowest dimension of the data, where you can generate a low rank representation with singular value decomposition. So what you'll do is the vectors represent most of the variance in the data, and you can drop then the variance, the vectors that have lower variance. So we can actually represent the data in a lower space. I Oh, that's the question. I'm going to get on with this a little bit, and hopefully some of the questions will be answered as we get into this a little bit more. I'm also conscious of time. Okay, right. So if we square the singular values, that actually and divide by the sum here, this actually tells us the amount of variance that was captured on each of the vectors. So the eigenvalue, the singular values and the singular vectors are paired such that the first singular value is paired with the first vector. So on the first component here, we've captured almost 77% of the data. On the second, we've got 18%. So if we just kept only that first component, we would be explaining most of the variance in the data. If we keep the first two, then we have basically 77 plus 18. We have 95% of the data. So we can reduce the dimensions of the data and just look at those two. Okay, let's have a quick look at if we actually run this using one of the many functions within R. We actually see this is doD.pca is the function to run PCA within the AD4 package. And again, we see the exact same thing. The total inertia here is basically how many vectors we have. So what's the rank of the matrix? It's 4. We have here the eigenvalues, and we have the projected variance here. So we've got 77 on the first axis, 18 on the next. Okay. And we can actually visualize this. We can also look at the actual, the V and the D matrix, and I'm pretty sure okay. This is interesting actually, because I've just realized there's a lovely function here, which is on Orchestra. It's actually linking to the newer version, but what's actually loaded in the actual help here is actually the older version that I have. So I just wanted to show you one other thing. This is the newer version here. So So if we take the U matrix, the singular vectors in that, and I'm just adding on here the names, we can begin to see the weights of each of these and the axis of these. So we see here on the negative side, we've got the crew wines. On the positive side, we've got the table wines. And we can do this for the SVD doesn't keep the row names and the column names, which is kind of a bit of a pain. But equally, we can see here the negative scores on the first dimension here are negative, and the, excellent and good, which is where the crew is up there on the negative side, is basically associated with excellent and good, whereas the positive end of PC1 here has actually got mediocre and boring, which is also where the positive ones are here. Okay, and we can plot. Where's this? The scatter. And this, we can actually plot it. So here are the eigenvalues. It's just a bar plot of the eigenvalues. So this is my $D, basically, the eigenvalues. This was 76%, 77%, 18%. So most of the information is in the first component. The first component, when we plot is the horizontal. We can see here that the boring and mediocre have positive scores. They're on the positive side of the axis, along with the table wine and the brand wine, whereas the excellent and good here are on the negative side of the axis, and they're associated with the crew and the ground crew. With principal components or any SVD, we can flip the sign on the axis. We're not interested in whether it's positive or negative. What we're looking at is the direction and the distance from the origin. So these here are projected in the same direction, and they have a great distance from the origin. Equally here, these are projected in the same direction and distance from the origin. And that's basically what's separating it out. Okay, so one little quick thing here, which is if we go in via help here, it seems to be that the version of the vignette that's shown seems to be an older version than actually what I have up here. So this is May, let me see here. This is saying the 1st of May. This is in, wait a second, but this is missing. Yeah, this is definitely the older version of it than this. So maybe I didn't change the date, which I apologize for if I didn't. But if you look at the actual version on the GitHub page, I actually have more information. So if you want the more up-to-date version of the vignette, please do have a look at the one that's on the vignette on the actual GitHub page, because I talk here about the actual matrices in a little bit more detail. And this was the command here that I ran, where I just linked the row names with the U matrix and the col names with the V matrix to make it more easy to interpret these from SVD. Okay. And we can also pull out the actual PC scores as well here. Okay. Now, SVD has a ton. You can compute principal component analysis using linear regression, using eigenanalysis, or even using SVD. There's a lot of different ways to do it. But SVD has some properties that actually make it really nice and efficient and stable when computing principal components. And one of these is that this U matrix, I'm just going to make this a bit bigger, this U matrix and the V matrix, the singular value matrix, are orthonormal. And what does that mean? Well, that means if we actually multiply it by its transpose, we get the identity matrix. Okay, what's the identity matrix? I'm sure most of you know. For people that like hated high school algebra and matrix factorization, it's a matrix where everything is 0 except for the diagonals, which are 1. Okay, so I want you to actually prove this. So I'm going to give you a second to catch up on the actual vignette, and also to show that when you actually take S dollar U transpose and multiply it by U, and equally the V matrix multiplied by its transpose, we get the identity matrix. Okay, so let's go do this. If you are following along and you have the Wine data set, great. If you haven't been following along, please still do this and just generate a fake simple data set. Do SVD in it, and please show that when you actually multiply U by its transpose and V by its transpose, we get the identity matrix, because this is a really, really cool trick in SVD. Okay, oh, sorry. Okay, I'm going to give everybody a second just to do that. Jenny, do we have any questions?
Yes, it does look like there are some in the Q&A.
Okay, so while people are doing that, let's just address some of the questions.
There's
okay.
2 more at the top.
Okay, my eyesight's getting worse. It's bad.
Yeah.
Okay, so wait a second. I understand how the scores are projected on the first 2 components, but I'm unclear how the wines themselves are given coordinates in the plot. I'm going to go into a lot of that in the next. So how the scores are normalized and the unit variance aspect to this. it basically, I think in the next, I want to go into that exactly how you actually get the scores for the actual plot and how the scores, the norm vectors are plotted. But I'm going to talk about that in the next session. I just wanted to get the basic concept of singular value decomposition being a useful way to decompose the matrices at this point in time. Are there other feeds going to be available offline? There's a few at the same time. I don't know what that means. Do you know what that means, Jenny?
I think is that because we've got 2 workshops going on at the same time, or there's going to be concurrent talks.
Okay, so everything will be recorded, and these talks will all be put up on YouTube. And obviously the workshop material, everything's up on GitHub, so everything will be available to you to go through at your own time. We're trying to, with the meeting, we're trying to actually accommodate multiple different time zones and as many people as possible. I understand. Okay. I'm struggling to interpret the idea of PCs when the only information we have about each wine is the name. Wait a second. I think it just jumped. So what else contributes to the grouping? Well, I think this hopefully will become a little bit more apparent when we do subsequent data sets. With this one, I know that basically you've got the expensive wines and you've got the cheap wines, and this is the biggest thing that separates this out. And we see that the Cru wines, the Cru Bordeaux wines, which are the more expensive wines, the judges liked them more than the others. And we see that separation out on the axis. I will go into a little bit more how to actually find the groupings, and I'll talk a little bit more about how to select components as well. Okay, is there a way to know when I've actually addressed these? Or
I've marked the ones as answers, I think.
Okay.
Multitasking here.
It's important to only show some features. So in this case, it's a tiny data set of 5 by 4, so all the features are shown. But yes, if you were doing an RNA-seq analysis and you've got 20,000 genes, you're obviously not going to label all of those. And I have some plots in the slides where I'll show where we just label those that are at the extreme ends of the axes. Okay, I think we will move on. Did
so.
Everybody work that out? Okay. Okay, so I will just go to this here, and I'll just do, if we take U, we know it's a 5 by 4. If we multiply it by its transpose, it's a 4 by 5, so that should work.
So we're not seeing your screen.
Oh.
You need to share again, I think.
Okay, share it. Sorry, I forgot I took it off sharing. Okay. So, okay, share screen. I'm just going to share the entire window. Okay, right, let me just show you that. So if we go to, you can see it now, RStudio. So if we multiply, and this is the same for whichever we do, if we multiply here the singular vectors in V by its transpose, we get this matrix here. Initially you think, oh, those aren't 0, she's lying, it's not identimatrix. Well, if I just round it, these values are actually really, really small. We can see that we have the identity matrix. And so that's a really, really, really powerful thing, one of the things that we use in PCA. Okay, so if I go to the rest of this vignette, I'm just going to show you, I show basically how to do it in pre-comp, getting the same thing. Okay, so in summary, in this section here, what we did was we took the Bordeaux data set, we scaled it, we centered it, and we scaled it. We did both, center is equal to true, scale is equal to true. Then we applied SVD to generate the 3 matrices, and we showed that this is actually the exact same thing as running duty.pca. We see when we do this, we actually separate the table wines from the Grand Cru wines, that the first component on the horizontal here represents 77% of the variance. We can see this in the bar plot here. And we can also look at the V. So the U matrix here was the wines. The V matrix here is the actual scores. And we see if we look in the same direction from the origin, so the positive end of the origin, the table wines were associated with boring and mediocre scores. Whereas the Grand Cru, we're looking in the same direction from the origin, are associated with excellent and good scores. And this Bordeaux here is actually neither associated with excellent and good or boring and mediocre. It's pretty much bang in the middle. Okay, we could begin to look at the second component then to say, well, what's actually separating those wines that are mostly separated on the vertical axis, axis 2 here, and we can see that it's separating out the table wine from the brand wine. And if we look to see what are the actual variables here that are most associated in the V matrix with separation on principal component 2, we can see it's boring and mediocre. So the principal component 2 separates table wine, which is boring, from brand wine, which is mediocre. Okay, so that's basic, simple interpretation of principal component analysis. Okay, so what I want to do now is I want to go on to the second one, which actually goes into component and principal component analysis and the different variants of it in a lot more detail. Okay, so this will be the second one, which is this here. It's called BPCA. You can also find this if I go into packages here. I can find, if I put PCA up here, I'll find the PCA workshop. I can click on user guides, vignettes, and I can click on the second one here. And I'll just click on HTML here to have this open. Okay, it's just taking a second. While it's doing that, I want to go back to the slides. So just to repeat, we basically have left and right singular vectors and singular values when we apply SVD. Although I'm describing SVD, principal component analysis can be computed by linear regression. In fact, when Carl Pearson described principal component analysis the first time in 1904, or was it 1901? It was via linear regression. We can also do it via eigenanalysis. I'm going to show that in a second, or some latent factor analysis. The vectors that we get, this is the U and the V matrix, can be called principal components, principal axes, latent vectors, eigenvectors. But whatever approach we use, whichever mathematical approach we use to generate these matrices, we're capturing the variance, or we're generating a low rank representation of the data. We can decide how many components we keep by looking at that bar plot of the eigenvalues, the singular values, and I'll explain the difference between those in a second. Or we can look at what they call a scree plot, which is just a plot here of the values, but it's called scree because if we're looking at a mountain, that moraine at the bottom is actually the scree. And so basically you can see, well, where's the mountain beginning to level off? And this elbow in the plot, or these are also called elbow plots or scree plots, is where we tend to cut off. So we say it's leveling off here. Let's just take 2 components here or 3 components. This is an exploratory data analysis method. It is not testing any assumptions. There's nothing you can do that's wrong. This is just you exploring the data. Okay, so let's talk about different types of principal component analysis within R. So, and I'm going to explain some of these. So we're going to look at pre-comp, print-comp, and PCA, duty.pca. And this is how we can actually get the loadings, the scores, and the plots in each of them. So each of these have slightly different nuances. And as I mentioned, some of this, there's a lot of different terminology here, depending on how these are computed and also what field. So if we're talking to people that come from ecology, they talk about ordering the variables or ordination, whereas when we're talking to computer scientists, they'll often say dimension reduction. In psychology, people will talk about factor analysis more so. In math, we may be talking about eigenanalysis. So depending on where people come from, they may have different terminology, but the actual the goal that we're trying to do is always the same. We're trying to find a lower representation of the data. And in this case here, we've found that the small cars are different from the trucks and maybe the utility trucks here, the fire engines or whatever. Okay, so one of the things that you will identify really, really quickly is that there's two forms of PCA that people talk about. One is covariance PCA and the other is correlation, or PCA of the covariance matrix or PCA of the correlation matrix. And this can be really confusing, particularly for beginners. But it's actually quite simple. The difference is that the covariance-based principal component is just the SVD, or the singular value decomposition of the centered matrix, whereas the correlation-based PCA is what we just did. We're centering and scaling. That's it. Okay, and some of these methods in R, most of them are default to correlation-based PCA, but PrinCompare by default will actually run covariance. It will not actually center and scale, it will just center. And also we notice here PreComp by default, it will actually do center and scale equals true. So just check that if you're trying to reproduce somebody else's work and maybe there's a difference. And let me just tell you one thing where that was different. So this is a very recent paper, well, 2019. It's from a group in Michigan, Sun et al., and they compared, I think it's 19 different methods for dimension reduction in single cell omics. And they found that factor analysis and principal components analysis, some of the oldest methods that have been described, were actually the most efficient. But when I looked at their code, and kudos to them, like lots of like emojis here because they made all their data available. They actually ran PrinCompare and it was center equals true, scale equals false. So this, if you wanted to repeat it, it would be important to actually run the same type of principal component as this is a covariance based rather than correlation based. Okay. Right, so let's have a quick run through. I'm going to go through this pretty quick because a lot of it is just showing you what the differences is of the different methods. So these are the different ones that we show. This here is the how to actually extract the loadings and the scores from all of these. And in this case here, we're using a really simple little toy data set, which is actually just two variables, X and Y. Okay. It just literally is, I do head on P here. It's 100 dim, or the structure of P. We'll see here, it's got 100 observations in 2 variables. Like we could plot this on an XY plot and we'd be done. But for the sake of this, I'm just showing this really because we can compute it in our head. Okay. To show the difference here between covariance-based PCA, and I actually compute this using 3 different ways. I use the SVD of the centered matrix, I use the eigenanalysis of the covariance matrix, and I use precompute equals false. And you'll see that all of these generate the same thing, and hopefully that'll give you a better feel for how the actual norm scores and everything are generated. So this here is my SVD of my centered and not scaled matrix. So MX here is centered, but it's not scaled. And if I run the decomposition of it here, I can actually see that these are my 2 eigenvalues here.
Hey, Adine, sorry to interrupt. There's a quick question.
So when we look at the eigenvalues associated with the covariance versus the correlation matrix, we need to actually divide here by the dim here of X is just the sorry, it's just the rank of the matrix. So it's 100. It's 100 rows by 2 columns. I'm taking here the max of it, which is 99 minus 1. Okay, and then the square root of that. Sorry, and then I'm squaring it.
Adine, can you hear me?
Okay. So I'm just dividing by 99. So I'm taking my singular values here, and to convert them to the eigenvalues. Sorry.
Adine, I was just saying that there was a, oops. Okay, looks like Adine got put off. Can anybody else hear me? Give me an emoticon. All right, good. Well, we know that this is going to happen, so hopefully she will be back. There's a question on the Q&A about whether the scaling performs long transformation. Sadly, I do not know the answer, so we will see if she gets in. Okay, great, you can hear me. Well, while we're waiting for that, is everybody keeping up? Is any issues with running the workshop? Did everybody get caught up? All right, great. Hopefully, it looks like she's trying to get back on. We may have jinxed her. We just had a side chat about some organizers like, I keep getting kicked off. Do we have any other questions in the chats? Okay, good. Someone, scale, people have commented that the scale function does not do log transformation. Typically, that this is the scale that I want. It centers to 0 and adjusts the standard deviation of all the values. Okay. Anything else we can cover while this is going on? There was some issue where it seemed like we were not linking to the most recent version, but it seems like it's well enough that it's working. There's all sorts of fancy stuff going on behind the hood to have these Docker instances come up. And everybody, believe me, this is a much better from some of the early workshops I went to where people were bringing their own laptops and you were sitting in the room and people were running around with USB sticks to give you a package. So it has come a long way in the last 14 years since the first workshops that I've been going to. And then people would running their own, and then they have to install all the packages. So I do think this is a very good, and we would do this if we were even in an in-person conference. We've been working this way, so everybody just logs in and it's pre-set up and all the packages you need for a particular workshop are already loaded for you. Slightly the downside is then you don't have it working on your own machine, but we had some discussions, and I forget what it is. I'm not sure who's on here. If anybody want to raise your hand and jump on about how do you, if you've got this session, it's there, but if you've done your own work or made your own notes, how do you download what you have done? I've forgotten exactly how to do that. Does anybody know? There was somebody who knew what they were doing, said that you could SCP to copy into the session, but I'm not exactly sure how that would work. There should be a way to download, I think, directly from that RStudio instance. But again, I don't know. I don't know if anybody knows how. Would want to, I can bring you up on stage to show everybody.
PCA, which is basically SPD of the centered and scale data.
Adine?
Yeah?
We lost you for a while.
Oh, okay. Am I back?
Yes, you're back. I was up here doing a song and dance and talking about the very old days.
Do we need to start again?
Yes, I do. I don't actually know exactly what. Can somebody put in the chat where it is that you got lost? Because I think you were talking and I was trying to. I say, oh, there's a question, and you weren't hearing me, and then all of a sudden you blanked out. I'm not exactly sure where we were. If anybody can tell her what slide or where we were.
Oh no, I was talking to myself. Oh, how devastating. Can somebody tell me where I left off? Where do I need to start again? Where's the chat?
I haven't seen. There's a Q&A.
17. Ooh, just sent SVD. Okay, I don't know what that is.
Oh,
Okay, it's size 17. I can look at slide 17. Okay, so I was talking about the
yeah.
Sonatal method had used covariance-based PCA, and I was running through the covariance-based PCA. So how much of that did people hear?
I don't know. We don't have your screen shared up. Someone has a quick
I
question.
I was wondering how much of this the covariance-based PCA did we have? Did everybody see this or did not? This is the second tutorial here.
We got, I think, the second tutorial.
Okay.
I'm not sure how far in.
So basically there's a toy data set, and I showed that basically covariance-based PCA can be computed as SVD of the centered matrix, eigenanalysis of the centered covariance matrix, or using pre-comp with scale equals false, which is actually its default.
Yeah, so there's been some, they said that just after eigen on a covariance matrix, I believe you had just done a scale transformation on the codes.
1 second. 1 second. Let me just
And then while that, there's a quick question about how long would the Cloud Studio R instances be available? At least through the end of the conference. I think that they will actually be able to be generated anytime after that. Again, if you, after 8 hours of an activity, it'll boot you off. If you have got one going now, they said that, Levi had said, if you're still working and it's been over 8 hours, it doesn't boot you off in mid-work. It's just if it's been idle for 8 hours, it'll boot you off.
Okay, so what's going on here? AirMeet isn't happy with me at the moment.
Oh, are you not able to share?
I'm not able to share. It is literally just, it's going around, and it's not a Wi-Fi issue. I have full Wi-Fi, but AirMeet is just going around in circles here. I don't know. Can somebody from AirMeet just assist here for a second?
RK, are you there? I could put a.
It's going. I don't know what the best thing to do is.
Jenny, can you please ask her to refresh the browser once and try?
Was it to refresh your browser, Adine?
Okay.
Let's try that.
That's always a good one to go for.
And she'll have to come back. All right. Well then, how about those Olympics? Has anybody been watching? It's been lots of fun. Okay, here she comes back.
Okay. Am I back again?
You're back again.
Let's try. It did the full, like, going to the cute, like, emojis. Okay. Right. Okay, you need to keep an eye on time. We're going to run out of time. Oh, no. Okay.
So we got your screen.
So covariance matrix, we did it 3 ways. SVD of the centered matrix, the eigenanalysis of the covariance, and pre-comp. Okay. So basically this here is the code to do. I'm scaling the matrix P. We're using center equals true, scale equals false, and then I'm using SVD, and I'm just showing you these. This is basically my SVD $D. This is the diagonal. This is the singular values. I'm actually dividing here by the square root of the rank squared and squaring it, and that basically gives me my eigenvalues. Okay. Then we can also compute it using eigenanalysis of the covariance. So cov here is the covariance matrix, and I have the same eigenvalues. We can also compute it via pre-comp. Okay. Now, pre-comp by default gives you the standard deviations here. And so this was one of the reasons why I was going, what's the standard deviations? What's the relationship between standard deviations and the eigenvalues? And that's why I actually did this. And basically the singular values are the square root of the eigenvalues here. So we can basically square these and get the eigenvalues. So we see that using 3 different approaches, we recovered the same data. Okay, so this is basically 3 ways to do covariance-based PCA. Okay, and I also show here, and I'm not going to run all of this, how to actually extract my right singular values. So the right singular values of MX, which is the centered matrix, is this $V here. This is giving these singular values. If I look for the vectors associated with the eigenanalysis on the covariance matrix, I get the same values. And if I pull the rotation matrix from pre-comp, I also get the same values. Okay, so that's basically 3 covariance-based PCA done 3 ways. And I also in that vignette, we have correlation-based PCA. Okay, everybody's still with me, hopefully. Okay, so correlation-based PCA done 3 ways. We scale and center, very important, the matrix. So if we scale and center it, by default, scale does center equals true, scale equals true. We can recover the singular values or the square root of the eigenvalues and the singular values. Okay, and that's recovering the matrix. We can also, I wrote a little function here, which basically takes the input and generates from SVD and just this little summary here. So running this little mini baby function here, which actually takes the eigenvalues, the standard deviation, the percent variance, and the cumulative percent variance. Actually, I need to run P0 first, don't I? I don't think I did that. P0 here. Okay, so P0 is my SVD of my scaled and centered matrix. Okay. And I'm just going to take my little baby function here. This is a little function. It's taking this many factors and it's just doing curly brackets here. So this is my little function. And then if I run that on P0, I extract my eigenvalues, my standard deviation, the percent variance, and the cumulative percent variance. Okay. I can do the same thing on pre-comp. Important with pre-comp is to set scale equals true. Okay, and that here will give me my rotations, and here this is the standard deviation. By default, pre-comp gives me the standard deviation. If I want to get the eigenvalues, I have to square them.
Okay. Quick question, Nadine.
Yep.
There was about what is the difference between PR comp and prin comp, and then why are those values slightly different? So
one of the things that's useful to do is if you do, okay, so if I write PR comp, I try to find how it works. I can't see. So this is S3. It's an old method. So I can just write methods on it, and it will tell me what the actual full name of the method is. And I know, because I've done it a few times, that prin comp here is actually in the package stats. So if I put the package stats in front of it, 2 colons here to call the function, I should be able to see it. But it tells me it's not exported from the namespace. So it's a hidden function. So if you want to get a hidden function, you have to put another colon in here. And I can see what it's actually doing. So sometimes this is actually what's really useful to do. This by default is doing center equals true, scale equals false, and it's running SVD. Whereas if I look at prin comp, prin comp.default. This here has this function car equals false. Okay, by default, this will actually run covariance-based principal component analysis. And if you actually want to run correlation-based principal component analysis, you have to set cor equals true. And this is actually computing this via eigen, not SVD. Okay, this is kind of an older function that was actually originally written so that it was compatible with S.
All right. There is one more. Let's see if I can. Do you see that, Adine, if I throw this up, the question on stage?
Yes. You discussed the difference between covariance and correlation is whether you scale or not. When would you want to center the data? I think you always want to center the data, because when you're looking at principal component analysis, you're looking at that distance from the origin. And I'll talk a little bit about that more in a second when you see horseshoes. Is if the data is not centered, you won't see that differences between like the positive and the negative end of the axis, so you won't see something useful there. So you're always centering, and then it's a question, are you actually scaling to get the z-scored matrix, or are you just doing the decomposition of the centered matrix? I'm going to talk a little bit more about the pros and cons of principal component analysis. It assumes that the data is quantitative. It assumes that you can find linear projections in the data, and that's not always true, and that's not always the best approach. The other thing we can think about is when it's actually doing that decomposition, it's trying to find the maximum variance. And it's kind of in a way, if you came from the old days of yore in bioinformatics where we did everything in clustering analysis, if you did a hierarchical clustering analysis with Euclidean distance, that's kind of what a PCA is telling you. It's telling you the maximum difference and between the variables.
Okay, I'm going to sign off again. If there's another one to come on, I'm going to try just to, instead of coming on, throw it up on the screen at an opportune time.
Thanks a million, Jenny. I really, really appreciate you keeping on top of these. Okay, so the last one here is pre-comp. And so rather than belabor all of these, there's print-comp here as well. And I run print-comp on P here as well. And I'm showing in every case, this gives you the standard deviation. We need to square it to get the diagonal, to get the loadings.
Oops, we lost Adine again. She probably has turned off her notifications, so. It's interesting, though, she doesn't notice that she gets kicked off, like if she lost her internet. Erica, are you on?
Yeah, shall we talk about the Olympics more?
Yes. My favorite was the woman who fell down in her heat, got up, and still won.
Really?
Yes.
Missed that one.
It was a distance race, obviously.
Yeah, you can't do that in the 100-meter.
But so we had the question again about how long the Cloud Studio instances will be available. When you initially create one, like I said, there's kind of the 8-hour, it'll keep you, and after that it'll get kicked off. But I think that the ability to launch them, so if you wanted to come back and relaunch this one tomorrow, you could do that, right? You can launch them again and again, at least through the end of the conference.
Yeah, I think we can assume at least through the end of the conference, but I am trying to get clarification on that. So we will, if we get an answer on that, we'll put that in an announcement or in the event feed so people can see.
Okay. So did someone want to mark down where Adine was when she comes back on?
Before we forget.
Okay. Kevin also says in that workshops can be instantiated outside of the workshops. Oh, are you back, Adine? Oh, she was back and then she froze up.
Then she's gone. The good news is that we do have a 30-minute time gap between the next session, so we can run a little bit over if we don't get everything done. And if there's some follow-up that needs to be done, maybe Adine will host a table in the lounge at some point where people can drop in and ask her questions.
Okay.
Okay, what happened?
we jumped out again.
No. Where did you lose me this time? This is going to be like one of those.
Yeah.
Sorry.
Erica just said, though, that there is a 30-minute gap between the end of this workshop before the beginning of the next session. So if people want to stay and spill a little bit over if you didn't get through everything, we can do that.
I think it should be okay. We're kind of into the last half hour of this. So I want to kind of quickly go through principal component analysis and get us to a stage where we're just applying it to some single cell data. Okay. So
I do not know where you ended off. When I see you freeze, I'm like, oh, I got to jump on and do something.
Thank you, Jenny. I appreciate that.
So
I'm going to just kind of summarize what that whole tutorial has. So basically it does covariance-based principal components 3 ways. It does correlation-based PCA, I think it's 4 or 5 ways. And I showed that basically how they're all doing the exact same thing. And that we can compute covariance-based or correlation-based principal components using eigenanalysis or using SVD, but SVD has some really nice properties, and it tends to be more stable, so more people tend to use it, which is why I had the first tutorial, which was showing why what the relationship with SVD is in PCA. So one of the things that I think that's important to recognize is when PCA goes wrong. So we kind of show those plots there a few minutes ago where you saw, your nice biplot or your single plot, and you're looking at the distinction from the origin. Okay, but sometimes principal components analysis goes wrong, and so it's really important to recognize what those plots look like and how we might maybe fix that. So we wrote a little review last year, and this was with Lauren Shu, who's now a PhD student at Harvard Chan. And so this was looking at, and we just applied this to single cell data. And what we did was we did SVD, we did covariance, and we did correlation-based PCA of the raw counts, and this was just some single cell data, or the log counts. Now the raw counts, what we had in that was we had 3 cells.
We're not seeing your screen.
Oh, crumbs. You seeing it now?
Yes.
Okay, cool. So what we did, so there's we basically described this in this paper we published last year, where we actually did SVD, we did covariance-based PCA, which is the one that Sun et al. Was said that was actually good, and we did correlation-based PCA, we did it on raw counts, we did it on log counts, and we did it on this data that 3 different batches from 10x from single cell, from CellSeq or DropSeq, and on 3 different cell lines. This is the mixology data from Matt Ritchie and the Australian group. And basically we see here that if we do standard SVD without centering or scaling the data, we don't get good separation. This here is the origin. We see that all the data are clustered here on the negative side of the origin, and we're not really beginning to separate out the platforms. If we center the data, so we're doing covariance-based PCA, we're not really seeing that good clustering on the raw counts, but when we look at the log counts, we're beginning to see that separation of A, B, and C here. When we look at correlations, that's centered in scale data, we equally don't see, we begin to see slightly better, but we still have this kind of weird shape here, which is like a clam, or sometimes they call it a horseshoe shape, even though it's not really a horseshoe. Between the first and the second component, but when we do it on the log counts, we're actually seeing that difference. In all of these cases, we're still a very obvious platform effect here, where the 10x data is projected further from the origin than the CellSeq or the DropSeq. And so we looked at this a lot more, and basically this kind of plot here, this clamshell or this arch effect, is something that you see a lot in single cell data, and you even see it published. But this is actually, this curvilinear relationship between successive components is very, very well described in the literature, and actually Susan Holmes has very well described their instances of this. And actually I had this whole big Twitter thing where we actually we had a big chat about like horseshoes, or this Gottman effect, or arches in principal component analysis. And there's another really nice, James Morton has another really one where they make artificial data, and they show how you can actually create between the first component and the second component these kind of clamshells. And what you're actually seeing here is that basically all of the components are shifted on the first component. Maybe you can see it more on this here. On the first component, everything is shifted to either the positive end or the negative axis. You're not getting any separation on that first component. You're only getting separation on the second component. Everything is one side of the origin. So anytime you see that, the first component, everything is one side of the origin. Sometimes you'll see this on a third or second or third, but mostly it's the first and second component. That's called a horseshoe. And that means you need to do additional pre-processing of the data. And this, like Simone was saying, I've seen it with metabolomics data. And actually Susan has a great example of this horseshoe in voting patterns in the American government. Okay, so in that case, what you can do is you can do further normalization of your data, or you can look at other different methods for doing decomposition analysis. And so this is a review that we wrote many years ago. It was written in 2016, where we actually reviewed different types of dimension reduction analysis. And in this, we actually pointed out that one method, correspondence analysis, was actually designed for the decomposition of count data, where you have a lot of zeros, which actually describes single cell data. And because of that, we applied correspondence analysis, and we actually see whether we apply it on the counts data or the log counts data, we no longer see horseshoes. And we also begin to see that our 3 different platforms now are no longer being separated, and we're getting good separation of the 3 cell lines A, B, and C. And we've implemented correspondence analysis in the Corral package. So I want to describe a little bit about correspondence analysis. It's also called decomposition of the Pearson residuals, and I'll explain about other people that have actually put that in as well. So I'm going to do a quick review of the correspondence analysis, and then we're going to actually do some single-cell RNA-seq. Okay. So for this, there's a lot of little libraries here, so I'm just going to load these in. So this is the third package, the third one. So if I go in here, and if I go into the vignette, it's the third one. And I apologize for the background noise. Is everybody with me at the moment? Okay, cool. What we're going to do here is load the necessary libraries. Okay, we have a toy data set. This is the simulation data set, which was actually described by Jake Young, and I'm just actually going to do this. It was designed for the analysis, for the idea of comparing prints of single-cell RNA-seq data. And this data is actually, it's 5,000, not quite, it's 489 by 150, but there's 3 clusters and 2 batches in this. So we actually have 3 clusters, clusters 1, 2, 3, and we've got 2 batches. Okay, so the idea is we're going to apply principal component analysis and correspondence analysis to this and see which one does a better job of separating out the batches and which is better. These data are single cell data, so that means if we look at them here, we do a kind of a summary on it, there's a lot of zeros. And that's kind of very typical in a lot of single cell RNA-seq data, and people have been trying to correct it by logging the data, but there's several studies say that maybe this isn't the best approach. So we're just going to apply a couple of methods to it. Okay, so So let's just go through this here. So I have a little bit about what correspondence analysis is. It was first described in 1935 by Hirschfeld. It was later developed by the Benzac School in France in the 1970s. And Susan Holmes has written a really, really nice review of how the French school used this duality diagram framework. It's a geometric interpretation of dimension reduction. Michael Greenacre has written multiple books on it. And then there's also a Dutch school and a Japanese school of principal component analysis as well. My favorite book is Legrand and Legrand, and also Michael Greenacre's book, and I have those at the very end of the slides. Okay, so I have some of these books here. I have Michael Greenacre's book, I've got Susan Holmes' book, and I've also got Numerical Ecology, which are, if you want to know more about this area, that I would actually recommend. Okay, I've also got a whole load of different, if you go to the end of this, I know this is new for many people, so I put in a lot of references on this vignette. Okay, so let's do a little thing of what is correspondence analysis and how is it different to principal component analysis. So we just said the principal component analysis was an SVD of either the centered or the centered and scaled, so the Z-score matrix. By comparison, correspondence analysis is actually a decomposition of the Pearson chi-squared statistics. And how we generate that is the observed values here are just the actual values divided by the sum total. So we transfer the counts into abundances. So basically the actual counts we divide by the total and it gives us the abundances. So that's what PIJ is. Then we say, well, what would we expect for any single gene? What would we expect? So we can calculate a column weight, which is just basically the total of the column divided by the sum total, or a row weight, which is the rows divided by their total, and we get the product of that. And so the product of the row weight by the column weight is our expected value. And so then it's just observed minus expected over the root of the expected. Okay, and that's the transformation. So we're saying the expected value is basically the product of the row weight and the column weight, and we basically, and our observed is basically just the abundances, the counts divided by the total, and then this is the matrix we decompose. And that's it's a very, very quick analysis, and we actually find that it's actually a lot better for data with a hell of a lot of zeros, which tends to be metabolomics data and single-cell RNA-seq. Okay, I've got a lot more detail here on this. So this basically is calculating out my row weights, my column weights, my expected values, and my observed values. And so this is basically calculating these out, because sometimes I know these kind of things, it depends on whether you're visual or not, or whether you want to see the code. This is just calculating it out. Now, just like principal component analysis, correspondence analysis is implemented in a ton of R packages, in the CA package, in the Factominer package, is AD4, in the vegan package, in the mass package, and then made for one of my old packages. And so, trying to be as complete as possible, let's do correspondence analysis 4 ways. This is like, let's do them all every single possible way. So let's do it using the AD4 package. Okay, let me just get this data. Have I got MAT? Just check. I have MAT, okay, which is my single cell RNA-seq with my 3 batches, my 3 clusters, my 2 batches. So let's run it using AD4. I like AD4. It's a package that was developed in Lyon by Daniel Chazelle and Jean Thiolus and others. And it really, they kind of have this whole duality diagram, and it's very much built on the French school of ordination. Anyway, so we run correspondence analysis. It's really quick. This means I don't want to see the scree plot, and I'm just going to take 2 components. And basically here I can see my eigenvalues, and this is the projected inertia and the cumulative inertia. This is kind of a little bit more difficult to interpret here because it's based on what the total chi-squared statistic is. Okay. And again, with this here, we can actually get our row scores in French. So LI is lines and CO is columns, or our column scores here. Okay, and then we can plot it. Now, and in this case here, we begin to see our 3 clusters, and we see separation of our groups. This is interesting because when we applied, I forgot to show you this here, when we applied pre-comp to this, when we actually did centered and scaled, so correlation-based PCA on this data, okay, we keep a rank of 2, so we're keeping 2 components from this here, and this is basically the cumulative portion. The variance, again, is actually quite low with this. But when we actually cluster it, we don't see separation. So here are 3 clusters, 1, 2, and 3, and these are not separating by cluster. Instead, they're actually separating by batch. I'm coloring it here by batch instead of by cluster, and you can see that it's actually clustering by batch. And we're not separating it using principal component analysis, but when we actually do this with the correspondence analysis, which is, we actually separate it out. Okay. Okay. Okay, so this is the AD4 package. I show literally how to, this is the Explorer package and the Scatter package are just kind of other ways to visualize these data. But they have the ability to rotate the matrix or to just and to zoom in and zoom out, which is, and it kind of tells you what the actual cluster is. So that's kind of a nice little, that's Scatter 3D, which sometimes can be nice, particularly if you're trying to look at these data. Okay, right, have we got any questions? Oh, 1 second.
I don't think there are any new questions that have come up. I was actually just going to make a post and put it in, and so I was going to wait to the end, but just to show people if they've made their own notes in our Markdown files, or if you can make your own codes when you're running an RStudio instance, but then at the end you can download them to your own computer. I was just going to, I don't know if you want to show how to do that, Adine. I'm going to put a note in here on the chat as well. But or there's other questions. If you have content-related questions, please ask those now.
Okay, so I'm just going to bring a little bit through this again. So we also then run correspondence analysis using GLM-PCA, which is a package by Will Towns, which was published in 2019. This actually implements principal correspondence analysis as a generalized PCA of the Poisson of the Poisson model data. And so it actually takes a while to run. And because it's iterative, it's not determined, you have to set a seed if you actually want to get the same response back twice. If you want it to be reproducible, you have to set a seed because it's not determined.
We're also not seeing your screen anymore.
Oh, sorry. I keep forgetting that I've not shared screen, or when I have shared screen. Okay, so so we run GLM-PCA, which is from Will Towns in this here. And GLM-PCA is a generalized principal component analysis, and it allows us to actually state the model. In this case, it's Poisson count data or negative binomial data. When we apply GLM-PCA using a Poisson model, that's actually equivalent to running correspondence analysis, because basically it's a decomposition of the Pearson residuals. But GLM-PCA is an iterative method. It's actually not determined. So we either need to set a seed if we want it to be reproducible, or we need to run it a few times. Okay. So this basically does an equally good job of separating out the data. And then I also run correspondence analysis using Corral, which is the package we developed. And we've basically developed it so it knows about single cell experiment, and it knows about Seurat data, and it knows about the single cell environment, basically. It will also run SVD using Herbala, which is like a fast implementation of SVD, which I actually do describe. I have actually SVD here and Erbula. It's just a faster, it's an approximate principal component method that's faster. Okay. So I run Coral as well. It basically will run pretty quick as well. It will give you the same result as running AD4, but this is a little bit faster if you're trying to use single cell data. And I then do what I've done with all of the others. It generates the same plot, is we compare them all. Okay. And in this case, I'm just basically taking the scores from the V matrix in Coral, or the CO, the columns in AD4, and I'm just getting the correlation. And there, you know, as I said, with any of these, we can actually flip the matrices if we multiply by -1, but the actual data is the same. Maybe do a head on that. Okay. Okay, so it's the exact same data. It's just the orientation on the axis is flipped. And you can actually, Susan Holmes has a nice approach for actually working out flipped eigenvectors if you're trying to match between different dimension reduction approaches or different dimension reduction on different data sets. So this is me just plotting them, showing the output from Coral. The output from AD4 is the same. Equally, I use it with GLM-PCA. It's not identical, but GLM-PCA is an iterative method, so the actual values will vary slightly every single time you run it. But it's pretty much, it's 99.9. It's pretty close. I've got a couple of notes here on just GLM-PCA and kind of optimizing its iteration, because it will give you, it will flip axes, and it will, sometimes PC1 is PC2. It's just because it's iterative. Okay, so the next thing I wanted to do, so just to recap on this, there's a lot of different methods for running decomposition analysis. Don't stop at PCA. By and large, a lot of them, the methods, that they differ in how the data is transformed. Covariance and correlation-based PCA are just decomposition, or SVD, of the centered or the z-score matrix. Correspondence analysis is just decomposition of the Pearson residuals, or the observed minus the expected over the root of the expected. Okay, there's a lot of other methods that are out there. There's sparse implementations. There's NEPLs is a non-iterative least squared approach for doing PCA. Sometimes if you've got a big matrix and you just need to be able to just compute the first component, it's useful. NMS is a slightly different way that it actually does things. It doesn't have 3 matrices, it has 2, and it's iterative approach to find the dimensions, but it is not constrained to be orthogonal. If you remember, PCA and as well as correspondence analysis, when we multiply U times the transpose of U, or V times its transpose, we actually get that identity matrix. It's orthonormal. It's uncorrelated. So basically what we're finding is each eigenvector is a different uncorrelated trend with the second, and sometimes that's too stringent. And we want to find more subtle effects in the data, and NMF or fast ICA are both not constrained to be orthogonal, and those can actually be really useful. Anyway, these are all reviewed in this review and many other reviews. Okay, so I realize we're up at time. The final vignette here is basically applying these methods to some single cell data. And the single cell data is the ZengMix data. Okay, and so this is available in the bioconductor package duo clustering. And the ZengMix had different cell types. These are cell lines that were pre-mixed. They mixed 4 in equal measures, 4 in unequal measures or 8 in equal measures. And they're just different immune cells. And so this is a nice data set when actually looking at these different methods. And with this vignette, what we simply do is we look at the data here. We see that there's B cells and T cells. Here, there's B cells, there's monocytes, there's naive cytotoxic cells and regulatory T cells in the ZengMix4 equal. And that's the one we do. We apply PCA to it. We see this horseshoe effect here. This is the origin. And everything is on one side of the origin. And then we also, this is just looking at the embeddings in the PCA, visualizing for UMAP. It does tend to split. UMAP does resolve some of this effect. We speed up SVD with Herbala. And then we do correspondence analysis. We apply correspondence analysis to it. We see that we don't have that first effect on the components, and we do a slightly better job of separating out these cell types. And we also show it in a UMAP. Where's our UMAP? Our UMAP as well. Okay, and that's basically what's in this. I'm just going to stop sharing for a second. So I'm happy to stay on with anybody who wants me to take them through that, or I know if people have something else, we're at time. So what I'm hoping that is that you have a better feel for how PCA works, what the different forms of PCA are, what correspondence analysis, how this difference for PCA, and how you might be able to apply that in your own analysis. And I'm happy to take any questions or stay on for as long as people need. And apologies again for the couple of technical hiccups that we had.
Okay, so there were a couple of questions. One from before. Someone is wanting to know how they can get a fancy Corel hex sticker.
I haven't made them yet.
Oh no!
we
actual physical stickers.
Well, we've not printed them.
I wish you could go to Sticker Mule and order like one of each of all your different packages, but you can't. Just like you have to order a minimum of 50 for a particular one.
Sticker Mule is actually pretty good.
Were they?
And yes, it's because we haven't had in-person meetings. I haven't generated a whole load of them, but yes, I am.
Okay, there is one more. I do want to give just a quick little ending thing. So we do have half an hour until the main keynote or the beginning introduction. We have, because we're juggling different time zones, we decided to push off and actually have some workshops and stuff before we have the main introduction. So the main introduction and then the first keynote will start in a half an hour from now. One last thing, if people want to run off, I had put the note in. I don't know if Dean, if you want to share your screen again real quick to show people how to, if they're making their own notes in the R Markdown from the RStudio instance, or if you make your own file, you can download those to your own computer. And so that's useful if you've put stuff in or made notes and you want to keep a copy of what you've done, because that instance that you've logged in will die after 8 hours. But again, we have learned that after the conference is over, the conductor is always there and running, and you can launch any workshop at any time.
Yeah,
so if you wanted to do this
up all of the time. I have to say I just tend to copy and paste out of it into my own, or sometimes what I'll do is I'll actually just get the GitHub of it down and I'll just edit it myself. I haven't saved too many things out of Orchestra, so maybe you're better to describe that. I know Kevin this morning did a whole session on workshops and how to run them, and so that's another resource that people want to know on how to run workshops and how to get them running and if they've got any problems.
Okay, let's see. I can just show you this. I'm trying to share. This is not going to work super well, but I did put notes in the chat, and again, it's just where the little file section that you have, if you click on the files that you want.
Wait a second. I'll tell you what. Why don't you drive and I'll do it?
Okay.
Okay.
Good. That
so
way
I will. Okay. So I am now in my Orchestra session. I'm going into file.
We're not seeing your screen though.
Oh,
here it comes. Yes.
It should be. Yeah.
Yes. So go to files.
Yeah.
No, not that files. Over on the right hand side where you
Oh, files here?
Yes, the file browser. And then from there, you would click on whatever, like if you want to go into vignettes, wherever you created the files, if you've made comments on if you've saved them, then you can go to the more, the little there, and you can say export.
Okay, so that's really, really useful. So yes, so I have my version here. So if I had taken this and I kind of went, I don't know, line 43, I can save that here. I can click on it. I can click export, and I can save it now as my edited version and download it. And it will have my really useful notes in it here.
Okay. Yes, and so there was, let's see, a couple more questions. I will show this on the stage if you want to answer them.
So in single-cell RNA-seq example, you don't transpose the data before pre-comp compares to the other examples. This makes difference in scale or sample. Yeah, in single-cell RNA-seq, I don't like doing principal component analysis. Principal component analysis is designed for data that's looking very nicely, normally distributed, a nice quantitative data set. Whereas in single-cell RNA-seq, we have a really skewed data set with a lot of zeros. And even if we apply like our SCRAN or our SCATE or normalization methods, we still have this really, really skewed distribution. And correspondence analysis seems to do a little bit better at that. We actually have a paper which will hopefully be going up in archive pretty soon, where we compare correspondence analysis to other similar methods, some different Tukey transforms on data and how they actually compare. We haven't found like the one, ring that beats them all, but I do think that those transforms tend to be a bit better. If you're running principal component analysis, you can always center on the rows as well as centering on the columns and do any additional transformations you want to do beforehand. Is there any benefit negative to iterative clustering PCA results and removing the resolved clusters? Okay, so any iterative PCA has pros and cons. If it's not determined, I tend to find myself running it multiple times in case I ran into a local minimum problem, and then it tends to take me a long time to do it. So I tend to prefer determined methods, particularly for exploratory analysis, which should be quick. You can definitely, lots of people in early microarray days said, oh, just do principal component analysis, take the first component, send the eigenvalue on that to 0, and I've showed you how to multiply the V matrix out again, multiply out the matrix again, and now do SVD again. You can definitely do it. You can do iterative approaches. There's also a whole field of dimension reduction analysis for background, foreground separation. People's doorbells, how you can tell if the Amazon person is at your door versus somebody passing by the street. And they have a whole load of really, really cool methods, and some of them like DLAM and kind of these robust principal component methods where you find global vectors as well as local vectors in the decomposition. So this field is enormous. There's these methods are applied for everything from single cell genomics to facial recognition to, video streaming.
Okay, so that's all the questions. I don't know if, how long do you think it would run through any of the other stuff? We could probably stay on maybe about another 5 minutes.
Are you okay with that, Nadine?
I'm okay. Yes, I do have to be into the next session, don't I?
You do. Yes.
I do. So I probably can't stay on too long, but what do people want me to do? Just tell me and I'm yours.
Okay, we got some thank you. There is a chat question note.
Thank you for going through this. It's tough to keep on top of it all.
Oh, yes. That's why you did. It's definitely
nice.
better to have at least one, if not 2 extra people to help out on the back end. so what is it? I happened to use M3C a few days ago, and it's one and all-in-one to perform TSNE, UMAP, and PCA.
Yeah, so MC3, it's great. So I use both TSNE and UMAP. I've had some collaborators that prefer TSNE, some that prefer UMAP. UMAP has definitely advantages if you're taking the components into a subsequent analysis. UMAP it maintains the distances, whereas TSNE doesn't. So TSNE, it's not good to take the TSNE components into maybe a linear regression if you're taking something further down with it. And the perplexity optimization in TSNE can sometimes be funky. But UMAP has given us these fun spaghetti plots sometimes. So I think the field isn't as, we're still working out what is the best approach to use, I think. You can use chorales and correspondence analysis, just straight replacement into TSNE. We use choral TSNE or choral UMAP all the time. And in the single cell example, I can share this for 1 second. In the single cell example, do you see? Wait a second, have I got the wrong one? In the single cell example, we actually have, we're using plot embeddings here and we're running UMAP.
Okay, I don't think we're seeing your GitHub.
Oh, really? Okay, wait a second, let me just share the right thing then. I should have just shared the whole screen, which is what I'd been doing earlier. It's just simpler. Okay, yeah. So in the PCA example, we basically run UMAP here, and we show how to run the correspondence analysis and put it straight into UMAP. And with UMAP, you may need to play with the number of neighbors, whereas with TSNE, you play with the perplexity.
Well, I think with that, maybe we will say thank you to Adine again.
Yes, so sorry about the technical issues. I'm very sorry.
Yes. All right, and I guess we can end the session now, and we will hopefully see everybody in the main welcome session in 15 minutes.
Thank you.
Thank you.